Hello, and today we are going to revisit this idea about electron configurations. So I know we just learned how to do this in our last unit, but today we are applying the electron configurations to bonding. So we're just going to take it a little bit deeper, but you already know this, you're already familiar with this, so that should be nice. First of all, if you'll recall, these elements right here, the noble gases, remember how they are stable. They have a full octet, which means they have a complete 8 electrons in their outermost shell. So, for example, neon, if we look at the electron configuration and the orbitals here, we can see it has 8 electrons in its outermost shell and its second shell, and here the third principal quantum number contains 8 electrons here, and the fourth, the outermost shell here, contains 8 electrons. That's krypton, and these all happen to be noble gases. And you'll remember noble gases are extremely stable and happy, and they are very inert. They do not like to react with the other elements in the periodic table. They do not want to gain electrons. They do not want to lose electrons. They just want to keep their happy little octet intact. So for the most part, when we talk about all the rest of these elements, they would very much like to have the electron configurations of these inert noble gases because they are very stable. Now, one point to note, here you'll probably see I wrote Duet Rule. And that Duet Rule is for the sole benefit of helium, who does not have 8 electrons, but it is an inert noble gas. It only has 2 electrons. And so by satisfying that first orbital with satisfying and putting 2 electrons in that s orbital there, helium also achieves the special status of being very stable and very inert with its Duet Rule. So those are that's just an important thing to note. So our next question, how do we write electron configurations for ions? And that's a great question because you're going to encounter a lot of ions. Let's take some examples to understand this. Here we have potassium, and when we write potassium's electron configuration, potassium is basically argon with one more electron. That one more electron is in the 1, 2, 3, 4th principal energy shell. So we have argon with a 4s1, and that's potassium. Now, if you'll remember, we talked a little bit about this last unit, but potassium very much would like to look like a noble gas in its configuration. So it could either gain another 7 electrons to look like krypton, or it could simply lose the one it has and look like argon. And that is indeed what happens. Potassium, when it loses an electron, gains a +1 charge to it, and we have this extra electron hanging out there. And when we look at the electron configuration and how that happens, we have argon with a 4s1. If potassium loses that one electron, it then becomes simply argon with the electron configuration of argon. It doesn't actually become argon. It becomes, it has the electron configuration of argon. Argon still has 1 fewer protons than potassium. They're entirely different atoms. They're not the same atom, same element, but they do have now the same number of electrons, the potassium +1 and an argon. They will have the same number of electrons. So how might a different element behave? Let's try oxygen. How would it achieve a noble gas electron configuration? Remember, we're just looking at the electrons in the atom and whether it's losing or gaining those electrons. So oxygen on the periodic table is right here. If oxygen could gain 1, 2 more electrons, it could have the same electron configuration as neon. So here, if we add 2 electrons to it, we will come up with an oxygen that has a -2 charge. And if we look at the electron configuration, oxygen's electron configuration looks like this. The helium plus a 2s2 and a 2p4. If we add 2 more electrons to that, we would have helium with a 2s2, a 2p6, and that happens to be the same electron configuration as neon. So that is exactly how oxygen can obtain a full octet. So here are a few examples for you to try. Try chlorine. Look on the periodic table, figure out the electron configuration for chlorine. What would chlorine do in order to obtain a noble gas configuration? And try magnesium. See what magnesium would do in order to do that. And then write the electron configuration for each of those as ions. And then if you'll just pause the video, you can do that, and then come back on, and I'll give you the answer. So I know you all got that right. That was probably so easy for you. Chlorine becomes chlorine minus 1. It likes to gain an electron so that, as we see in the periodic table, it can have the same electron configuration as argon. Magnesium, on the other hand, is a metal. It's going to want to lose 2 electrons. Here we have magnesium. If it loses 2 electrons, then it will gain the same electron configuration as neon. One final question. Based on their electron configurations, how would magnesium and chlorine combine? How would they bond? What would happen there? And we've already explained how magnesium becomes an ion and achieves a stable octet, and how chlorine does. So if chlorine only wants to gain 1 electron, but magnesium would like to lose 2, they would combine in a way such that we'd have a magnesium atom and 2 chlorine atoms. That would satisfy both of the chlorine atoms. It would satisfy the magnesium atom. They would all be able to achieve stable octets, and they would form magnesium chloride, 1 magnesium with 2 chlorine atoms. So that is one way to look at bonding and how you can think about bonding in terms of electron configurations and the octet rule and how atoms combine those in order to bond.